time. So, do we start recording? Welcome everyone to the second week of the summer school. So this week we will have Tung Nguyen from Princeton telling us some recent developments on Erdős-Hajnal's conjecture. And Erdős-Hajnal's conjecture is one of the major conjecture, and Tung has done some amazing work on this one. So let's give it to Tung.
So thanks for the invitation and the introduction. It's good for me to be back here. I was an undergrad here until 2020, and it's been 4 years since I left Korea. And it was really great to be back to IBS. I mean, to meet wonderful people, and I am having a great time here. So thank you for coming. Okay. So I plan to discuss some recent work of myself and maybe some other people on the problem of Erdős and Hajnal, on the topic of induced subgraphs. And before I talk about this, let us just start with a very basic result of Erdős and Hajnal. And this was from about 19 years ago, so 1925. And the result says at the end of this graph, there's a clique or independent set of size at least about log n. And during this series of talks, I will use log for the binary logarithm. Okay. So this is actually the one of the beginning of Ramsey theory, right? I mean, the very basic results on Ramsey numbers. And as far as you, and I guess I mean all of you already know. Recently, in this 1/2 constant has been improved a little bit, right? But still, if you don't care about constants and you only care about the asymptotics of the growth of the size of the largest clique or independent set, then also early examples from random graphs show that this bound is asymptotically optimal, right? So it's not hard to show, and again, this theorem of Erdős 1947 shows a typical graph of n vertices. There's no clique or independent set of size at least 2 log n. So here by typical graph, I mean you take a random graph on n vertices and with edge probability 1/2, then you and as long as n tends to infinity, you will get this result. Okay, so it is not hard to show. So if you don't care about the constant factor, then perhaps for general graphs, I mean the growth rate of alpha or omega, I mean it's not there's not much to say about, right? But the picture seems to change dramatically when we start talking about graphs with a forbidden induced subgraph or graphs with a very strict local prediction. Right. So in this talk, also in this week, I will mostly concentrate on the notion of induced subgraph. So definition. So for a graph G, induced subgraph of G is a subgraph G of n while removing vertices only. So in other words, you have to preserve the edges between the pairs. I mean, as long as you want to remove an edge, you also have to delete its endpoints as well. Okay. Yeah, so let's go to some examples. This is a lot of easy examples to warm up. So first, I would like to talk about the 3-vertex path B3. So what are the structures? I mean, what is the structure? What is the structure of graphs with no 3-vertex induced path? Right. So let me say no B3, no induced B3. Means it's not hard to show that you can show that if you have no 3-vertex induced path, then every component has to be a complete graph. Okay. So what about 4-vertex induced path? So this is going to be an exercise for you, just like a warm up. I say, so no induced 4-vertex path means every component. So either the graph G is disconnected, or this complement, let me say G bar is disconnected. Okay. And yeah, so these are very simple examples that perhaps you say, maybe there's some hope that if you try to exclude some small graph as an inducer graph, then maybe you can describe the structure of the whole host graph. And of course, during this series of talks, I will always use G as a mixed host, as a mixed host graph. Okay. So yeah, but there's a question which seems to be still out of reach at the moment about C4, which is the 4 cycle. Can you describe the structure? Maybe some sort of decomposition or some structural description of graphs with no induced 4 cycle. And as far as I know, until recently, at least for now, we're still kind of pretty far away from such a goal. So structure or something, structure or composition. I think we still don't know what the exact answer to this question should be. Okay. So let me say in general. So for graphs H and G, let me say G is H3. If there is no induced graph of G isomorphic to H. Yeah. So if you do everything up to isomorphism, then you just say, this just literally saying that H is not an induced graph of G. Okay. And so for example here, no induced P3 means P3 free, and no induced P4 means P4 free. Okay. So so from these two examples, so now going back to the business of finding a large clique or independent set in the graph. From these two examples, it is not hard to show that. So P3 free and P4 free would give you a clique or independent set size at least group n, and here n is the number of vertices. right? So for example, in this picture, I mean, you're always expected to see, I mean, so maybe one of the components, which are all complete graphs, I mean, should have size at least root n, or you have at least root n components. And so you're going to see an independent set of size root n. And for these P4 graphs, you can show that by induction, alpha g times omega g is in this n, where alpha is the size, I mean, is the independence number, and omega is the clique number, and just by simple induction. So it all reduces to show this structural results, which would be an exercise. Okay. Right.
Can you write a little bit bigger?
Yeah. Okay, so what about C4? So we have a result of, I think, by Erdős and Hajnal. And first by Erdős and Hajnal, and then consequently by everybody else. Let me see, around the 70s. That if you're C4 free and releases, then maps of alpha or omega is a list n to the one-third. And if you want to try, then this will also be a nice exercise. I mean, and my hint here is just to take a largest independent set in the graph and now see how the independent set interacts with the rest of the graph. Okay. So one of my favorite open questions, I mean, which I am trying to advertise these days, is the problem of deciding whether this one-third exponent is optimal. So far, we still don't know, I mean, it's optimal, and I think it will be very nice if we can find a better argument than what Erdős and Hajnal did, or we can find a good example of C4 graphs. Right. Now, I mean, going back to again the business of alpha and omega, and how, I mean, the growth of rate of the size of alpha or omega changes with respect to n when you have some local condition. As you can see, initially for general graphs, I mean, these are all logarithmic in n, right, in terms of the size. And here, as long as you try to forbid, I mean, some induced subgraphs in your host graph, or if you try to impose some sort of local condition in the graph, then something changes, right? I mean, mass of alpha or omega will jump suddenly from logarithmic to some polynomial in n. I mean, just a small polynomial. So basically, n is some power. So, Erdős and Hajnal, maybe 50 years ago, made conjecture that perhaps this phenomenon, I mean, should go for excluding any induced subgraph, I mean, not just the simple graphs. So the conjecture formally says for every graph H, you can find some C positive, maybe small, but depending on H only, such that OH3 and n vertex graph G, we always have, you can always see a clique or independent set in G of size at least n to the C. Yeah, so in other words, in general, I mean, mass of alpha or omega will, of course, has to be the power of n. Any question? Okay, so this conjecture, I mean, is of course still open, and until today, I think, I mean, not many graphs H are known to satisfy this conjecture. I mean, only a handful way of construction can be found. That's the first, and also there is a I think there's a bigger question about trying to find a structural description or some decomposition method for all H3 graphs, which is still unreached at the moment. And as you can see from what I said earlier, this question is actually open for C4, and there's no structural description so far. It's similar to what we have for P3 and P4. Right. So and another point here is, this conjecture seems to be as far as I know, this conjecture and its variants are the only problems in graph theory saying something's going to happen if you exclude a general induced graph. Okay. And the point here is you're excluding only one induced graph and not 2 or 3 or infinitely many graphs. Right, and also, as you can see, as I started from a basic result in Ramsey theory, you could say this conjecture lies at the intersection of 2 branches of combinatorics. One is graph Ramsey theory, and one is structural graph theory. So from the point of view of graph Ramsey theory, you try to understand how much does the Ramsey number, the diagonal Ramsey number change under additional restriction. And from the point of view of structural graph theory, you would like to understand what's going to happen if you try to exclude some graph as an induced graph. Okay. And this conjecture is also a very nice statement about the local global phenomenon in graph theory. That says, as long as you try to impose some local condition in the graph, then something global is going to happen. Right. As I said, this conjecture is still open, and investigating which graphs H satisfy the conjecture remains one of the main challenges in graph theory. So let me say H has the Erdős-Hajnal property.
There is one question from Zoom. Is this still open for bipartite graph H?
Yeah, that's definitely still open for the general bipartite graph H. Yeah, I think a good case is for all path. When H is a 6 vertex path, for example, then it's still open. I mean, we'll go into that later. We'll go into this topic maybe in a few minutes. So H has the Erdős-Hajnal property if it satisfies the conjecture. So the first result that I want to communicate in this talk is a very fundamental result of Alan Pat and Seymour from maybe 20 years ago, in showing a very simple but very efficient way to view graphs with the Erdős-Hajnal property from smaller graphs. So Alan Pat and Seymour. Let's say now I have 2 graphs, H1 and H2, with the Erdős-Hajnal property. And I have a vertex V, E, H1. Then the graph H obtained by substituting H2 for V in H1. Also has a property. So here what do I mean by substituting? So let's say I have a graph. So here's my graph H1. And here's V in H1. Okay. So now I look at the neighbors of V in H1. So this is let me see. Yeah. So now by substituting H2 for V in H1, I mean by removing V, then I'm going to take a copy of H2 and then I add it to the remainder of H1. And then I'm going to make everybody in H2 adjacent to all of the neighbors of V in H1. Okay, so in other words, so here's going to be the leftover of H1. This is going to be the neighborhood of V in H1. And this is a copy of H2. And what I do is make everybody in H2 complete to everyone in H1. Is it clear? So just for a simple example, let's say there's a way to get the 4 cycles C4 from this operation. So I'm going to start with the 3 vertex path. Okay, and what I'm going to do is to substitute a copy of the edgeless graph on 2 vertices for this right-hand side vertex. So what I'm going to have is this graph on the right-hand side, which is exactly the 4 cycle. Okay. So this actually gives, if you look at this, if you use this theorem, then this actually gives another proof that C4 has the Erdős-Hajnal property. Okay. Right. So now let me go into the proof of this result. So I would like to go a little bit deeper into the proof because the idea behind it is going to be relevant in the next 2 talks as well. So my plan is to go through the proof of this first, and then I'll try to develop a little bit throughout the next 2 talks and maybe today as well. So let me go through the rough idea of this first. So the idea here is trying to generate lots of copies of H1 inside a big host graph G. Okay, and in order to do so, let me try to rephrase what it means for a graph H to have the Erdős-Hajnal property. Okay, so here's the observation. Okay, so the observation is H has the Erdős-Hajnal property. If and only if there exists, let me say an integer. Let me say k, at least 1, such that if G G is H3, then max of alpha G omega G raised to the power of k is at least the number of vertices of G. So I'm going to use this notation to denote the number of vertices of G. Okay. Which means if I denote this by Fg, for example, then this actually means if the number of vertices of G is bigger than Fg raised to the power of k, then G as a copy of H. And here by copy, I mean induced copy. Does that make sense? Right. So, so for the rest of the proof, I'm going to use this observation. Okay. Right. So from now on, let us, just forget about alpha or omega, and let's just treat this function f as some sort of general function on the graph G. So the idea here is as follows. So the Erdős-Hajnal property of H1 and H2 would give you integers K1 and K2 with this property, right? And now we're gonna set K later. But let us say that now we're trying to prove the Erdős-Hajnal property of H, and K is a very large number depending on H, and maybe H1 and H2. And now I want to assume that the number of vertices of the host graph G is much bigger than this quantity. Now I want to show that G actually has a copy of H. So what am I going to do? What I'm going to do is I will look into a small subset of G. A small subset of vertices of G of size Fg raised to the power of K1, where K1 is the integer that is given by the Erdős-Hajnal property of H1. Okay. Maybe 2K1 or K1 so let me say 2K1 means so that this number is bigger than the Fg to the K1. And let me say this subset is S. So what I can infer from this is F the number of vertices in S is going to be Fg raised to the power of 2K1, say, and this is bigger than the same function of GS, and also raised to the power of K1. Sorry, at least, okay, and this is bigger than f of G restricted to S raised to the power of K1. And also, I'm going to use this notation to denote the subgraph of G induced on S. Okay. So we have this chain of inequality. And what this means is S is going to contain a copy of H1, right? So GS has a copy of H1. And the point here is this is true for every vertex subset S of G of this size, right? So we can find a copy of H1 here. So far so good. And because this is true for every subset S of this size, now we can try to generate lots of copies of H1 G. So now by simple double counting, you can show that the number of copies H1 G is, of course, at least, let me say, G choose H1 divided by G minus G raised to the power of 2K1. Sorry. Fg raised to the power of 2K1 G minus H1. Choose Fg raised to the power of 2K1 minus H1. Okay. Now, I guess maybe many of you are familiar with this expression, right? And then the next obvious way is to apply the very simple inequality to deduce that this in the left-hand side is going to be at least G divided by Fg raised to the power of 2K1, and altogether raised to the power of H1. Right?
Could you explain a bit about the double counting again?
Okay, yeah. So here you take any vertex subset S of this size, right? And if you look at the subgraph of G induced on this subset, then by this chain inequality, by the definition of A1, you're going to see a copy of H1 inside this induced subgraph. Okay, so what this means is, no matter what vertex subsets X you choose, you're always going to see a copy of H1. So now what you want to count is the number of let me say H1 and S. Right. So using H1 might not be a good quotation, but then let me say Fs, where F is actually when you use a graph of G isomorphic to H1, and S is a vertex subset of G of this size and containing F. Right. So now we count by two sides. So of course, by what we have just said, this number is indeed at least G choose FG to 2K1, right? Because for every F there is an F, right? And now if you fix when you use a graph F of G isomorphic to H1, you want to count how many S can contain this F, right? And the number is of course at most G minus H1 choose F of G raised to the power of 2K1 and this is 1. Good. Any other question? Okay, so now going back to this business of counting copies of H1 in G. So now here we know this is at least the amount of copies of H1 in G. So now how to generate a copy of H in G? I guess everybody is happy with this picture, right? I'll try to erase it. Go to the next step. So now we have this many copies of H1, and now we're trying to generate a copy of H by using H2. So what do we want to do? So the idea here is to among all of these copies of H1, for each of them, I will try to fix the vertices representing H1 minus V. And I will try to see how many copies of H1 are actually extending this copy of H1 minus V. So here, let me say this is a copy of H1 minus V G. Right? And now I would like to ask in how many ways that this copy of H1 minus V can be extended to a copy of H1 in G. And in order to do so, I will use this inequality together with the fact that which is trivial, that is there are at most G raised to the power of H1 minus 1 copies of H1 minus V in G, right? And so together with this expression, what I can infer is, again, by a similar double counting trick, that there has to be a copy of H1 minus V that can be extended in G divided by the G raised to the power 2K1 times H1 raised in G to a copy to a full copy of H1. Makes sense? Yeah, so at least what I can say is there has to be a copy of H1 minus V for which this set of vertices, I mean the set of candidates for V has size at least G divided by G raised to the power of 2k1 times H1. All right. So now I want to generate a copy of H2 inside this subset. The point here is if I can get a copy of H2 inside this set of candidates, then we win, right? Because this copy of H2 together with this copy of H1 minus V will form a copy of H in G. I'm done. So what I want to achieve here is I want this quantity to be at least f of G raised to the power of 22 or maybe 2k2. Right? Right. So if this inequality holds, then the proof is completed. So this is equivalent to G at least of G raised to the power of 2k1 times the number of vertices of H1 plus 2k2. Okay. So finally, number k here is going to be 2 times k1 H1 plus 2k2. This is basically. Any questions?
Is there any improvement of this bound?
Yeah, that's a very good question. I don't think so. I mean, so actually, I mean, if you do a little bit better with the proof and try to optimize the things a little bit, then you can remove the crossing factors too. Yeah. So I think in general, I mean, it seems to me that K1 times H1 plus K2 is the best that this proof method could give you. So the point of this result is to merely show that the Erdős-Hajnal property is preserved under substitution, but maybe it has no, not much hope. Not much hope of optimizing the exponent. So very good. Right. Yeah. So that's about the proof of the Allen-Basel-Moshe theorem. So I want to. So what I want to stress here is actually the idea of counting, not only counting induced subgraphs, I mean counting the number of copies of a particular small graph in the host graph, but also the trick of fixing the quotient of a copy of a graph, and then try to look at the possible candidates for the other vertices in a copy. I mean, this idea will be developed in the next two talks. Right. So now going back to this business. So substitution is actually an interesting notion in structural graph theory. And as you can see, I mean, this actually resembles how you multiply numbers together, right? So you can actually so the way you can get a graph by substitution is similar to the way you can get a big number by multiplying two small numbers. And so people have, actually people from the structural world have come up with a notion for graphs that cannot be obtained by this operation from smaller graphs. So let me say the definition. So the graph H is prime if it cannot, be obtained by substitution from smaller graphs. So in other words, there are no graphs H1 and H2 whose number of vertices is strictly smaller than the number of vertices of H. Such that H is so H, let me say H can be obtained by substituting H2 for some vertex of H1. Okay, so for example, as we discussed earlier, the 4-cycle C4 is not prime, right? Because it can be obtained by substituting the 2 vertex axis graph for the middle vertex of the 3 vertex graph. Good. So actually, I mean, from this theorem, you can say that the quest to verify the Erdős-Hajnal property of all graphs H reduces to verifying the Erdős-Hajnal property of all prime graphs H. So so where are we so far? At least verifying the property for some small prime graphs H. Is that possible? So we have some results. Let me say these are the collection of theorems over the years. So of course, P4, the 4 vertex path is a prime graph, of course, and it has the Erdős-Hajnal property. So it has the Erdős-Hajnal property, and it is also the only prime graph on 4 vertices. So what about 5 vertex graphs? There are 3 prime graphs on 5 vertices. The first one is the pool, which is this configuration. The triangle with 2 pendant edges on top. The next one is the 5-cycle, C5, and the last one is the 5 vertex path V5 together with this complement graph, which is the house, this configuration. And of course, since we are talking about the Erdős-Hajnal property here, you maybe you already realize that it suffices to consider pairs of complement graphs, right? Because the graph H has the Erdős-Hajnal property if and only if complement does. Okay. So these are the 3 prime graphs on 5 vertices, and actually it took a couple of decades just to verify the Erdős-Hajnal property of these graphs. So let me do a bit of survey here. So the bull was done by Chudnovsky in Sopra. And the thing that is very special about this configuration, the bull, is the proof that Chudnovsky and Molissa did actually gives you the exact optimal exponent for the size of the largest clique or independent set. So you can actually do G to the 1 order. And so what they prove is you can always find a clique or independent set of this size at least. And an exercise which may be useful for you. I mean, after we have discussed the substitution business, is to show that this exponent is optimal. So show that on further family tree. Okay. The next part, C5, it was one of the original techniques of Erdős and Hajnal for the conjecture, and it was done a couple of years ago by Seymour. Let's start with Seymour and Sophistico. And the video was just published last year. And P5 was also a target that perhaps frustrated several people in the area, and it was done very recently, just last year, by myself with Alessandro and Cosimo. Right. So this actually means the current state of the art about small prime graphs. So at least for now, we know that all 5 of X graphs have the Erdős-Hajnal property. And there was also a question of Tung whether you can show that there is any prime graph on at least 6 vertices with the property. And it was also answered in the positive last year by the 3 of us. And we managed to show that there actually infinitely many prime graphs with the Erdős-Hajnal property. So basically, when I think that's all that we have known about graphs with the property. Okay. So I think before the break, I would like to give another exercise, which is actually pretty interesting and also related to the substitution idea for Erdős-Hajnal. So as you can see from the statement of the conjecture, I mean, at least from what I just told you a few minutes ago, the conjecture says that if you forbid any graph H is an induced graph, then you can always find a clique or independent set of size at least G to the C, right? So if you have a post graph G and with no induced copy of H, then there has to be a clique or independent set of size at least G to the C for some constant C depending on H only. But if you look at the Wikipedia page of Erdős-Hajnal, then it is a little bit different. The point here is what it says is, so let me say, this is the Wikipedia version. Again, H3, G, then massive alpha or omega, massive alpha and omega is at least asymptotically some power of G. So what this means is there exists, right, theta and C positive depending on H only, such that massive alpha omega is at least theta times G raised to the power of G, raised to the power of C. Okay, so that actually means there's actually a slight discrepancy between the 2 versions, which is this constant factor theta. Now the next exercise is to show that these 2 versions are actually equivalent. So that the G to the C version is actually equivalent to the theta G to the C version. Right, so immediately you can see that the first version implies the second version, right? You can just choose eta to be 1. And that's good. And now the interesting part is to show that, I mean, this eta version actually implies the first version. Does that make sense?
With the different constant,
No, so
with the different C.
yeah, with the possibly different C, so maybe C prime. Okay. So I think we should stop for the break and be back in 5 minutes. Yeah, so welcome back. Yeah, so the remainder of today, I would like to discuss a bit, discuss some results of density, which could be relevant in the next couple of talks. And so, as we already discussed, the Erdős-Hajnal conjecture is actually, one of the purposes of this is to understand what the general properties of an H3 graph are, right? And so, what can you say about an H3 graph in general, or any induced subgraph, any forbidden induced subgraph H? So, and so far, we still don't have many theorems like that, but one of them has been quite useful, which is the result of Rödl from 1986, if I remember correctly. So Rödl, 1986. He says for every epsilon sufficiently small, but let me just say from 0 to 1/2, and for every H, if G is H3, for every H, then there exists some delta depending on epsilon and H, in positive, of course, such that if G is H3, then there is a vertex subset S in G size of this delta times G, and the subgraph G induced on S is epsilon sparse or epsilon dense. So what do I mean by epsilon sparse or epsilon dense? So epsilon sparse means mass degree of G restricted on S is at most epsilon times S, and epsilon dense if this holds in the complement. So in other words, the mass degree of G complement restricted on S is at most epsilon times S. So what it says is, the S distribution of an H3 graph in general will be very disruptive. You can actually zoom in a very distant portion of the induced of the whole graph, right? You can shrink the graph, the host graph, by just a linear constant factor. So an induced graph which is very sparse or very dense. So this is actually a very nice result, and one of the earliest applications in graph theory of the regularity lemma. So, so in what follows, I'm going to sketch the proof of this result. Okay, I'm not going to go with numbers because actually we'll see a better version of it later or maybe tomorrow. But for now, let me just try to sketch the proof of this using the regularity lemma. So, so I guess maybe all of you already know about the lemma, right? So it says, given any density parameter epsilon, right? So what the regularity lemma says is if I have a regularity parameter epsilon in the lower bound and on the number of parts. So what it says is you can output a big number and depending on epsilon and small m, such that in any host graph G you can partition the vertex set, the whole vertex set of G into at most big M and at least small m number of parts, such that but an epsilon fraction of the pairs are epsilon regular. Okay? So then for any G there exists, let me say K between and small m and an equipartition of VG. Let me say this partition is V1, V2, VK, such that for the utmost and epsilon fraction of pairs ER VJ are epsilon regular. And I'm not going to go into the detail what epsilon regular means, but I would assume you mean maybe all of you already know about it. Okay, so yeah, so here an equipartition. So we want to BK is an equipartition of VG if the size difference of every two of them is at most one, right? Okay. So so the proof of this is actually so to prove the theorem of Rödl using the regularity lemma is not too hard. And the key idea behind this is to choose M and let me see epsilon prime to be sufficiently good depending on the origin of epsilon. Then we will try to output the linear constant delta. Okay, so right, so here's the partition. It's my epsilon prime regular partition. Of G, and also the number of parts. So this M, where epsilon prime and M are to be chosen depending on epsilon later. Okay. So the point here is almost, all but an epsilon fraction of the pairs in this picture are epsilon regular. So the first step is to use Rödl's theorem to extract 1 over epsilon prime parts in this picture, so that every two of them are epsilon prime regular to each other. Right. So there exists 1 over epsilon prime parts pairwise epsilon prime regular to each other. Okay. Yeah, so now let me assume that these are the 1 over epsilon prime parts that are epsilon regular, that are epsilon prime regular to each other. So now, point about the regularity lemma here is you have the epsilon prime regularity, but you don't know anything about the density of the pairs. So what I'm going to do is to classify pairs into 3 types, right? Very sparse, very dense, or middling. So basically, all of these epsilon prime regular pairs will be of 3 types: sparse and with some constant. First, middling and dense. So now our situation is very similar to a Ramsey problem, right? You have a complete graph, and then for every pair, you have one of three choices. So what Ramsey theorem says is you can extract, right, a decent amount of parts such that every pair has the same type. Right? So every pair means all the pairs are uniformly sparse or uniformly dense or uniformly middling. So now we use Ramsey theorem. Next part is to use Ramsey theorem based on this classification. Okay. And now then, let me try to say, so now these are, as every pair in this picture are now epsilon prime regular, and at the same time, they are all sparse, or dense, or all middling. The point here is, we have shrunken the graph just by a constant factor, right? Because as I said, we were going to choose epsilon prime and at the end as functions of epsilon. So yeah, so now we have three outcomes, sparse, middling, or dense. If all of them are sparse, then we are good because this is going to be this epsilon sparse outcome, right? So you have many pairs pairwise sparse to each other, and if you combine all of them, you will get a sparse induced graph. And the same situation for dense as well. All the pairs are dense, and now their union is again a very dense induced graph. And if all the pairs turn out to be middling density, and now there is a very familiar trick from the regularity business, which is to use the embedding lemma to embed a copy of H among these pairs. Right? Actually a rainbow copy of H, and the reference here, I guess maybe some or all of you are familiar with is something similar to the triangle counting lemma. So embedding lemma or triangle counting lemma. Okay, so that's
When you have a sparse case, do you pick one vertex from each pair or
the sparse case.
yeah.
So the point is when I am in the sparse case, I don't care about the density inside each of the parts. I only know that every pair is sparse. So with some calculation, I can say their union has to be sparse. So I'm not constructing any copy of H in this case. So I'm only gonna construct a copy of H in the second case of the density using the regularity and something similar to the embedding lemma or the triangle counting lemma.
So the edges in the back doesn't matter.
Yeah, they don't have.
Because the clique found is really large. Right?
Yeah,
You can ignore the image.
so that's probably the idea. And of course, we have to fill in the numbers. Right. So so there are two things about this proof method. The first thing here is in the last step when we use the embedding lemma or counting lemma. This proof, this step actually not only gives us one copy of H, right, but it gives many copies of H. Many copies of H inside the whole strategy. And if you work out the numbers, then this actually a function of epsilon, or to be more precise, a function of delta. So that's the first observation from this proof idea. And this was, I think it was recorded in a paper by ECOPRO from nearly 20 years ago. And it says that, so in Rödl's theorem, here the condition is H3. And what we can say now is we can replace this H3 condition by a condition that says not many copies of H. So theorem by ECOPRO from 2006, that says, so we can change H3 to at most, let me say delta times G raised to the power of H. Copy of H in G. And the same conclusion holds. Okay. And the point here is in this step, when we constructed H, we not only get one copy of H, we get also many copies of H. And this is the number, and this is the number. Okay. All right. The next point here is, of course, I mean, if you know about the regularity lemma, then you see that the dependence of delta on epsilon and H, I mean, and in this case, epsilon is really bad in the sense that it is tau type. And this connection to the Erdős-Hajnal conjecture is that if you look at these two outcomes, epsilon sparse or epsilon dense, in these outcomes, if you pick epsilon to be a very, to a very small power of G to the -1, so if you pick epsilon to be G to the minus C for some very small constant C, then you would recover a clique or independent set of roughly this size, but now with delta changed to be a function of G. So basically what this amount to say is since the dependence of delta on epsilon resulting from the regularity proof is really bad, you're not going to get something much better than the logarithmic bound that you already have from the original Erdős bound. Okay. So, and people in the area already noticed this phenomenon some time ago, and there was a conjecture being first proposed by Princeton that says in Rödl's theorem you can actually force delta to be a power of epsilon. And if that is true, then you would get Erdős-Hajnal. So conjecture. By Princeton in January, that says for every H, there exists some analysis in D, and this one. So here D is supposed to be huge. In contrast to this small C. So some huge D such that if G is H-free, then there exists some S of size at least epsilon raised to the power of D times G. So that G restricted to S is epsilon plus or epsilon dense. So in other words, in Rödl's theorem, you can choose delta to be the power of epsilon. And to see how this implies Erdős-Hajnal, you can just take epsilon, I think to be G raised to the power of -1/2D.
There is a question from June. Is there a version if change forbidden H to forbidden a set of H's, for example, forbidden or A plus B vertices with E edges, bipartite graphs? I mean, maybe one part has a size A vertices and B vertices, and between them there are E edges. So maybe the question is asking if we forbidden all of these type of bipartite graph as an industrial subgraph, then can we expect more better statement?
Not that I know of.
Okay.
I guess I mean the general question for bipartite graphs is still open. So
Okay.
and I mean I mean, asking for an exact number of edges seems a bit too much. Or maybe what the question is asking is to forbid all the partial graphs have the same number of edges and the same
Maybe
type.
maybe that is the same number of edges
Oh,
between them.
I think I haven't thought about it. But I know it. Thank you. So let us go back to this possible conjecture. Is it clear? The symbol is clear, right? So let me say H has polynomial Rödl property. If it satisfies this conjecture. And then you can see the polynomial Rödl property implies the Erdős-Hajnal property.
I have a question. So in the Rödl's theorem, the condition is that GS is epsilon sparse and epsilon dense.
Or yeah.
Also in both cases,
Yeah.
we only need one of
Yeah,
the
yeah. And for sure, if epsilon is too small, then you cannot have both of them, right? Yeah, so what it says is exactly one of the two outcomes has to happen. So
So when you have epsilon to be g to the -1/2d,
yeah,
then if you plug in, you get a, like for instance, you get an epsilon sparse graph. The maximum degree is bounded by.
so I think the trick here is to apply to Rand's theorem. You have it.
Yes.
Point here is, I mean, you want,
Yeah.
you want to be sure that the size of S is still much bigger than 1 over epsilon, so that you can apply to Rand's theorem. So I think I don't have much time, so let me just introduce, one last property before we start for today. So yes, so far this condition only concerns H3 graphs, right? And we have talked about the polynomial property. But as we discussed, there's actually from the regularity proof, we can actually recover the theorem of clique, which concerns graphs with not too many copies of H instead of H3 completely. So what if we ask for something similar to the polynomial Rödl property, but with not many copies of H instead of H3? So there's a property that says H is viral if there is D, at least one, such that for all epsilon from 0 to 1/2. So similar to yeah, so here I forgot to say epsilon is from 0 to 1/2. Yeah. So here H is viral. Again, there is some constant D supposed to be large, depending on H, such that for every epsilon to 0 from 0 to 1/2. If G at most epsilon to the D times G raised to the power of H of piece of H, then we have the same conclusion. Then there exists S, robotic subset S of size at least epsilon to D, G, and GS is epsilon sparse or epsilon dense. Okay. So here we have the observation that the Weyl property is going to imply polynomial polynomial property, and implies the Erdős-Hajnal property for any bar H, right? Okay. So let me just comment a little bit about these three properties. So Erdős-Hajnal says if you exclude some graph H, then you're going to see a large clique or independent set. And actually, this says a lot about the post-graph G, right? Because we're trying to impose some local condition on G, and now we get something back about size largest clique or independent set in G. That's the first thing. But if we go to the polynomial Rödl property, then now the post-graph G is a bit less relevant because of the presence of the density parameter epsilon. I mean, G is still H3, but now what it says is we can actually shrink by a very good factor, such that we can get a very sparse or very dense induced subgraph. And here, everything depends on the density parameter epsilon, right? But G is still, but G is still important in the sense that G is H3. But now if you go to the Weyl property, then G becomes even less relevant, because here the condition H3 is now replaced by not many copies of H, and here again the count, the number, depends exclusively on the density parameter epsilon. And the reason that I say that G is even less relevant is because this function G raised to the power of H is actually a trivial upper bound on the number of copies of H, and so everything depends on the density parameter now, right? And so it is not too hard to see this indication, and maybe tomorrow I will present a proof recently by Fox and Fak, showing that these three properties are actually equivalent. And the proof uses the container method and the idea from the proof of the Alan-Passer-Limouchi theorem. Any question?